If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in machine series. So today again we will be solving 5 questions starting from question number 86 to question number 90. Okay, then let's try to solve these 5 questions. Now if you come to question number 86, the 1 kVA 230 by 100 single phase 50 Hz transformer having negligible winding resistance and leakage inductance is operating under saturation. You have to be careful, it is operating under saturation. While 250 by 50 Hz sinusoidal supply is connected to the high voltage winding, the resistive load is connected to the low voltage winding which draws the rated current. Which one of the following quantities will not be sinusoidal? Okay, so for a single phase transformer, if you give primary as a sinusoidal voltage, so your secondary will also get sinusoidal, so you will get sinusoidal output because your voltage should be sinusoidal. So your phi, because phi is equal to n d phi by dt, so that is also always sinusoidal, so your phi is also sinusoidal. So if you take this phi as a sinusoidal, now this phi is generated due to this current. If you give load, then the current will come, then that current will generate your phi. In nodal also, that phi will be your magnetization current. Okay, if you see your BH curve, BH is nothing but B is, you can think of that is phi, because B by A is equal to phi. So if you divide it by A, it will get, and H is equal to Ni. So N is a constant, so you can think it is a graph of phi and I. So if you increase your I, your phi will increase, but there is a saturation. It is operating at saturation, that is, it is operating in this region. Saturation region means after some time it will get saturated. So when it gets saturated, then to change it a very little, you have to give more and more current. So from here to here, if you want to change, you can see here it is linear. If you change little bit, I correspondingly phi will also change. But if you come here, if you change a I from here to here, then this much phi will only change. Phi will change very small, but I is changing this much. So you will need more. This portion is linear. If you increase I, then correspondingly your phi is increased, no problem. But when it goes near saturation or going to saturation, then if you increase more and more I, then there is a little change in phi. So to change phi, you have to give more and more current. So what happens, because it is working at saturation, means if you just switch it on, then even with little I, it will go to saturation. It is going to this one very fast, because they are saying that it is operating under saturation. So when you increase your phi little bit, then only it is going at saturation. I little bit it is going. So if it goes saturation, then to change this phi from here to here, you have to be from here to here. If you change the, because your phi has to change, that is rate of change of flux, that will be E. So because your phi is coming from E, so phi has to come, and because phi has to change, so it will draw more and more current from the system. So it will draw a very peaky current of this fashion. Initially it will be linear, first portion, then it will be peaky, then also it will be something of this current. It will be very high current, peaky current. So it will not be a sinusoidal, it will be of, initially it will be linear going to, then it will take a peaky, then finally again, so it will be of this fashion, very peaky. So it will be peaky in nature. Why? Because you need more and more current. As it going more towards saturation, you need more and more current to change a little bit in phi, because you need to continuously change this phi, because E is already changing, so it should be. So current drawn will be more peaky in nature. So that is the current drawn. LEDs will be always same as sinusoidal. So current drawn from the source will be more peaky and peaky. It is not load current. Load current will be again sinusoidal. So the peaky portion, from that peaky portion, sinusoidal portion will go to load current, and rest of the portion is needed in the magnetization, because this current from source has two parts. One is supplying load and one is for magnetization to maintain that phi. So that load part is sinusoidal, plus that if you add that current for this magnetization, that is IM current, then you will get this overall current, which will be a peaky in nature. So that's why it is option D. Now if you come to question number 87, a 400, 200, 250 Hz 3 winding is connected as shown in the figure. The reading of the voltmeter V. So if you see this dot polarity, we have already discussed this dot polarity in protection. So this is of this polarity. You are connecting your voltmeter between this and this, and this is your 400 volt. This is 400 winding, this is 200, this is 200. So voltage across is 200. So this is the dot. So we have discussed, if current is entering through this dot terminal, then it is plus. If it is leaving through dot, then it is minus. So here also you can see the current is entering through this, so it is plus minus, because it is the supply voltage. So you can take this as a reference. So it is, if you think that current is coming from this side as a reference, so this is plus, this is also minus, and if you come here, the current is leaving through dot, so it will be minus. If it is leaving through dot, then it is minus. If it is entering through dot, then that terminal will be plus. So now if you add from here to here, you can say this is 400. If you take KVL, because this is the voltmeter, you will be getting, this is your voltmeter. So 400 minus 200 minus 200, answer will be 0. So you can start with minus 400 plus 200 plus 200 equal to V. Suppose this is your V. What is the total voltage from here to here? So that is 0. So your voltmeter will read 0 voltage. That is option A. Now if you come to question number 88, the single phase transformer has a maximum efficiency of 90% at full load and unity power factor. Okay, the efficiency at half load at the same power factor. So if you take my output as a OP, suppose, so maximum efficiency, that means your full load constant loss and copper loss is 0. So at that output full load, that is full load output is OP, and your constant loss and copper loss both are same. Suppose I am considering both as a I, that is equal to 90% given, because at maximum efficiency your constant loss equal to copper loss. So that iron loss both I have taken as iron. Now the efficiency at half load at the same power factor. Power factor is again unity power factor. So your output will be now divided by 2, and this will be output divided by OP divided by 2, plus constant loss will be same, but your copper loss will be divided by 4, because you are getting half load. So it is divided by I square R copper loss. So if I is getting half, so loss will getting 1 by 4. So that is, so from here if you calculate your OP will be, you will get 18I. If you apply 0.9, this is equal to 0.9, then do a little bit side change, you will get this answer. You put it there. So it will be 9I divided by 9I plus I by 4. So I will get cancelled. You will get your answer as 87.8%. That is your option D. Next in 89, figure shows an ideal single phase transformer. The primary secondary coil are wound and on the core as shown. The turn ratio this, the correct phasor voltage E1, E2 and the core flux. So if you do this phasor diagram, there are two conventions. General convention, what we do, if you give a supply voltage, this is your phi. So if you give your supply voltage, suppose this is your V you have given. So if I take it is a ideal, so whatever V, there is no loss, so entire V is coming here. Otherwise V minus this drop will come here. So that V, because this is the supply voltage V, actually this is your V, and the voltage induced here is E1 and voltage induced here is E2, and your terminal voltage is V2. So E2 minus this drop is equal to this, V1 minus this drop is equal to E1, and this E1 E2 both generated due to this flux phi, due to this electromagnetic induction. Okay, so this is your phi, this is your V phi. So generally what we take E1 E2 this side, E1 or E2 as per their ratio. If it is 1:2, 1:1, whatever, here it is 1:2, so obviously E1 would be more than E2, half of E2. So if you can think of this one, this is E2 and this is E1, because E1 is more, E2 is less. Okay, so this is one way of drawing this one. There, because there is no loss, you can consider this E2 minus, there is no drop, ideal loss, so that will become your V2. So E2 will be equal to V2, and this E1, that is generally what is the idea why you will do this one, so that you think that the power is flowing from V to E1. That's why this 180 shift is given, because the angle between this phi is generating both E1 and E2, so they should be at same phase, because both E1 and E2 is generated due to this phi. So both should have same this, wherever it stands, so E1 E2 will be same. This 180 shift is given to give an idea, because the power is flowing from this to this side. One can think of this one in this way also, if you, because both are correct, this is also correct, these two ways this phasor diagram can be represented. Because if you do KVL here, so V is equal to E1, no loss is there, so this V becomes E1. Once it becomes E1, because E1 is generated due to this phi, so E2 is also generated due to this phi, so E2 will be also in this phase, so that is also V. And here this is resistive load, so whatever V2 I2 will be in the same line only, so I2 will be here only, but I2 will be more because current ratio is the reverse ratio, so it will be the same phase, so I2 will be more, and because E1 is there, so I1 will be also in phase, because I1, because no ideal, in ideal transformers I am taking magnetization current as 0, no magnet, it is negligible magnetization current, so that's why I whatever I2, that same I1 is proportion is coming. Otherwise I2 will come here with proportion plus that Im will give you I1, that is not required. So both these are correct, you can think of this way. So whatever you do, V should be, your phi should be lagging this voltage V, and if you take KVL, V is equal to E1 and E1 is equal to V2, so this is also correct, this is also correct, this is what it is representing just 180 degree shift means power is just flowing from this to this side, that is this one, or this one you can write minus E1 also. They give it V1 is equal to minus E1 so that it gets idea, but the magnitudes will be remain same. So both these are correct. If you can think that power is flowing from this side, then this phasor diagram will be accurate. And to indicate that power is flowing from this side, so that's why V is given higher angle and E1 is given lower angle, so that power flows from this to this, that 180 shift is given. So this is in option A, so that's why it is the answer. You can check this one, but it is not. E1 E2 should be on same, that should be very easily seen because they both are generated due to this phi. So this is already gone, either of this, and phi is on this side always because V is, because if you are going to this notion, then V is equal to E1 and phi is lagging that voltage, because whatever supply voltage you give, magnetization current will be 90 degree lagging this IM. Now if you come to question number 90, the figure shows delta 2 star connected 3-phase distribution transformer used to step down the voltage from 11,000 to 415. It has two switches S1 and S2. Under normal condition it is closed, it is open, so A, B, C all are connected. But in superior condition, one S1 is closed, S1 is open, this is closed. Okay, so when you close this one, then they are asking between the voltage across A and C. So they are asking VAC. So what is VAC? VA minus VC. VAC, because VA is the phase voltage, because it is star connected, so it is VA minus VC. So phase voltage, line voltage will be different. So what will be VAC? You can see whatever voltage you are getting between these two, it is VAB. And what is this winding getting? What is VC? VC is this voltage, VA is this voltage. So VA is getting from this one. So this winding is getting VAB and this winding is getting B. If you on this one, so B is coming here, it is getting BBA. So you have to be careful about, suppose this is my VA, VB, the supply side. So it is getting VAB. VAB divided by turn ratio will give you VA, small VA. Because small VA, this voltage is getting this much voltage divided by this turn ratio, whatever ratio. And this VC will be getting BBA divided by turn ratio will give me VC. So that you have to be careful. Okay, because this is getting this much voltage, so divide by this. Now what is the turn ratio? I explained you turn ratio, you always take whatever voltage it is getting across this winding, 11,000. Whatever voltage it is getting, it is not 405 because it is line to line. So this voltage is 405 by 13, 450. So the turn ratio N is here 11,000 divided by 415 divided by root 3. So this is your turn ratio, because the voltage across this, voltage across this is whatever line voltage, voltage across this is phase voltage, because A to ground. So it is 415 by root 3. So if you do this ratio, as per that ratio it will come, so no need to think or you calculate this one. So what will be your VA? So VA will be, you can think now, VA will be same 415 by root 3 because it is 11,000, so it will be divided by that ratio 415 by root 3 at an angle of, what is this angle? If you take this one as a reference, then this is 0, this is minus 1, just opposite to this one. So you can think of this is 0, this is 180, or you can write it plus 30, this is 120, this is again 30, so you can think it of 150 minus, this will be 415 by root 3 at an angle of minus 150. You can do it in this way, no issue, or you can do it because both are just opposite to each other. So if you subtract this one, it will be ultimately getting added, this minus this, because they are just opposite. So if you do x1 minus x2, so because x2 is negative of this one, so it will just get added. So ultimately both these things will be added, so you will get answer 417.2 angle 30 if you do this one. If you make it 0, then magnitude is this one always. So that is your option B. If you like the video, then press the like button and please give your valuable comments in the comment section.